was invited to the teacher enrichment program just a couple weeks ago, and I had to do a presentation again. But it was easy for me because I've been in a couple of high schools doing some STEM programs. And so that was exciting. We did a space science presentation to get students interested in STEM. So this is the first time I have a group of teachers. This is really exciting. I wanted to talk about aerospace systems engineering. I know it's not really a science subject, but I hope I make it interesting. It's really important to Northrop Grumman, the aerospace systems engineering area. So we're going to talk about that. So my agenda tonight is how did I get involved in the aerospace and defense industry? What motivated me to get involved in this? Then we'll look at Northrop Grumman on the leading edge of. We'll look at what kinds of products and services Northrop Grumman provides. Then we'll go into aerospace systems engineering, and I like to think of it as architecting a whole that is greater than the sum of its parts. And then finally, I'll close out with Northrop Grumman's commitment to STEM, and I left in each one of the brochures a copy of the Northrop Grumman corporate website that can point you to where the educational resources are located and what Northrop Grumman does to promote STEM within a whole pipeline that we talk about from K-1 all the way to K-12 and beyond to the university level. Does that sound good? Started? All right, my career in the aerospace and defense industry. Why did I have a desire? Well, I thought these jets were awesome. I really did. I thought these jets were awesome, right? But there was some things that were going on. My father was in the aerospace industry, so there was some motivation there. And he worked for a company called U.S. Chemical Milling. And U.S. Chemical Milling back then, when the industry was looking at reducing weight of components, they didn't have the technology we have now back then. They had to actually chemically mill aluminum sheets of metal to reduce weight, and they were doing that for this strategic bomber for the United States Air Force, B-58 Husky. And what they would do is they'd take that vertical stabilizer that you see there, and in order to make it more lightweight, they'd actually chemically mill it, reduce material from it through chemical erosion, if you will, to actually reduce the weight. That's how they were doing it back then. And my dad, well, eventually the B-58 was canceled, and U.S. Chemical Milling went out of business. And my dad was the last trustee of the company when it filed for bankruptcy and closed the camp. They closed it down. I had an opportunity as a young boy to go through that whole facility and see all those empty cabinets and chairs and everything there, just empty. And then in the back lot, there were these big vertical stabilizers. I thought, that's really cool. Well, he got a job with North American Aviation, and that was really cool too. So he went to North American Aviation around the time of Kennedy, President Kennedy, and they were starting the space program. But North American Aviation also had a strategic bomber, the XB-70. And one day they brought it out for static display out at Edwards Air Force Base. Anybody familiar with Edwards Air Force Base? A lot of testing going on out at Edwards Air Force Base. Even today, still a lot of testing goes on. And it was a static display. And I was about 8 years old. And my mom, me, my sister, my dad, and my brothers, we all got to see the XB-70. And I was just, I got to get this. I love this. I love this business. But I wasn't really smart in high school. Maybe I wasn't motivated in high school. The problem, motivation, smarts. I had the smarts, but okay, I'm going to join the Air Force. That's the best way to get involved with jets. So I joined the Air Force at 19. I'm the technology part of STEM, right? Start out with the technology part. So I joined the Air Force at 19 to learn how to work on jets, aircraft, technical training jets over 4 engines. B-52, by the way, had 8 engines. But I got to learn that, and I joined the Strategic Air Command. I was assigned to March Air Force Base, and I was a crew chief. Yes?
What level of math did you get through in high school? Or did they teach?
I had to in high school. I had high school math through Algebra 2, but I never got into calculus. I had the trig, but I never got to the point where I took calculus. And I regretted that. I eventually caught up with that. But at the time, I went through Algebra 2, trig, geometry, but calculus was to go to university, and I never took calculus.
Okay.
That's what I did. So I became a crew chief flight mechanic at 20. I had an airplane. I was responsible for 4 years, General Mullen's airplane as a crew chief, and I got to fly in it quite often. And we used to call these the boomers, and it would provide aerial refueling. And this was the B-1 bomber during the 70s that was in development. And Jimmy Carter, of course, became president at that time. And he kept it going for a number of years as they went through the development program. So this was really exciting time for me early on. But after the Air Force, I joined the space program. So I spent 4 years in the Air Force, and I got to work on the two preeminent human space flight programs that NASA had, the Space Shuttle and the Space Station. And this was a great opportunity for me. How many of you all knew that at one point we were going to launch shuttles from the West Coast? We were going to launch shuttles from the West Coast at one point at Vandenberg Air Force Base. And they spent billions of dollars, the Air Force, to develop a facility that would allow us to launch shuttles from Vandenberg Air Force Base. That's what it was in the 80s, and basically when we lost Challenger here out of Florida Space Coast, the Air Force decided that they couldn't put, if you will, all their eggs in one basket. And they basically decided to go down the Evolved Expendable Launch Vehicle program, which allowed them to launch their national assets on expendable launch vehicles. And that's what we have today, the Atlas 5s and the Delta 4s. I did get to participate in the first SDS launch out of Rockwell International in Downey. And Rockwell International Downey now is basically, I'm not even sure what it is anymore. I mean, it was a facility that had probably at the max, probably 10 or 15,000 employees at that point. And basically during the whole shuttle and the B-1 program, and then basically after all the development efforts, it went down, and today it's no longer. So I actually ended up then going on to the space station program, and later on in my career with Rockwell, and worked the electrical power system, and eventually I migrated my way to KSC, and I got to KSC, and I got to work as a test project engineer and project leader at Kennedy Space Center. And so it was the Air Force that really started me on my academic journey of learning. I am the T in STEM initially with the aircraft maintenance technology, and then I had a bachelor's degree from Southern Illinois in aviation management. I thought, well, I don't want to work on airplanes, I want to fly them. So I did a little pilot training and did the aviation management. But I got hired by Rockwell, and I did look back. It was just a great opportunity to work in the space shuttle and space station programs. I did get a master's of science in technical management, which has a lot to do with what I'm going to talk about tonight. It's along the lines of systems engineering. I did pick up an MBA from Pepperdine, all courtesy of Rockwell International at the time. And I have a master's degree from this great institution in space systems. I decided also to get my master's degree in industrial engineering from Florida, Central Florida, University of Central Florida, and I have a certificate from Caltech in aerospace project management, and I got a certificate from Boston University in financial planning. There's a lot that goes on in program management now. They've got to know about a lot of financial numbers as well. So, well, the space shuttle program, as we all know, came to an end after we lost Columbia. The decision was made basically to complete the International Space Station. All the components of the International Space Station would go up with the space shuttle. And once the space station was built, the shuttle fleet was going to be retired. It retired a couple of years ago. I left before that. I left in 2006. My position at KSC was I was the project leader of the cockpit avionics avionics upgrade program. We were going to modify all the space shuttle orbiters with modernized avionics, because they were designed in the 70s, they were flown in the 80s and 90s, in the 2000s, but we wanted to really bring the orbiters up to modern aviation standards, so they put me in charge of the cockpit avionics program out at KSE to do all the integration and testing of those components. But when we lost Columbia, they decided not to go through that, and then I decided to take a position with Northrop Grumman as a program manager.
Can I ask a quick question?
Yes, sir.
You're clearly on the inside when it comes to knowing about the shuttle and the shuttle program.
Yes, sir.
Had we not lost one or two shuttles, would we still be flying them?
That's a good question, and even back in the promise of the shuttle in the 80s was such that the cost associated with the shuttle mission was a lot lower in terms of the estimation than it turned out to be. It turned out to be a much more complicated vehicle than we anticipated, and so a lot of money was spent to maintain and repair and configure the orbiter. So it cost a tremendous amount of money each time the orbiter landed, and you'd have to do the turnaround operations to get it ready for the next subsequent mission. So because of that cost, I think it probably was going to end at some point, because it was just so prohibitively expensive to continue to operate that particular machine, especially one of the 70s and 80s. Hence, that's why we were trying to modernize it. The airframe was good for 100 missions, each airframe. The airframe had no issues, but the avionics, the electrical systems, the computer systems, they were all starting to get outdated, and the idea was to incorporate a tremendous amount of new technology into those orbiters, but it would still mean the cost. And so I think the national decision made was to retire and move to the next vehicle. So when I took my position, I changed really tracks here. I got more down and in on payloads, so I was doing a lot of systems work at the Kennedy Space Center, but I got down into payloads working on ISR programs, intelligence, surveillance, and reconnaissance. And this is what we're doing over here in the facility. It's just a few miles away. We're doing the Joint STARS program, but we also have a number of these kinds of programs as well, where we're looking at laser technology, we're looking at multispectral imagery, we're looking at various technologies, and these technologies are to look for mines. So that was very important during the time where we were surging in Iraq and Afghanistan, because most of our guys and gals were getting killed or injured by mines, especially on the ground. And so there was a big push to try to find technologies to search for mines that were recently buried, or also search for mines that are in the waterways. So we have some technologies at Northrop Grumman that allow us to search for mines on the ground, as well as search for mines in the sea lanes to keep our harbors clear, to keep ocean channels clear. And we're doing that for the Coast Guard. I checked that, the U.S. Navy, and we're doing that for the Army. And then we were doing a little bit of work for JPL in looking at underdense vegetation penetration with some LiDAR capability. So real high-tech stuff going on at Northrop Grumman, but I got to have some fun too, right? So I got to go out to Yuma Proving Grounds to do some testing with the gimbal on a UAV. They like to call them drones in the media. I'm not sure why they call them drones. I don't like that term. But it's a what we call a vertical takeoff UAV, and we did some testing at Yuma, and we actually raised a dummy tank, and we were able to fire a missile at it to prove that the capability was there to not only find mines, but also delays in support of our warfighters to attack an enemy tank. All right, Northrop Grumman. We're on the leading edge of, I think, missions that are important to the nation. We obviously want to be a leader in preserving freedom and advancing discovery. So we've got a lot of portfolio in the aerospace systems business. Supply high-value mission products to protect our national security. There's obviously a defense component, large defense component within Northrop Grumman. But we also do a lot of space systems. Deliver Earth and space science products to both the civilian science and military users. So we do a lot of that And we do also protect communications for the warfighter. We actually do a lot of work with Harris and vice versa with respect to assured communications and protect the nation with reliable global missile warning and defense. So providing our customers with high impact, best value aerospace products and systems through a good quality system, innovation, and superior program performance. Northrop Grumman today, leading global security company, almost $25 billion in sales in 2013 and near $37 billion in total backlog. Our leading capabilities are with unmanned systems, Global Hawk. We have a good understanding now of the cybersecurity threats that we all read about in the media sometimes. So what are we going to do about that as a nation to protect our infrastructure, our IT infrastructures, our networks and so forth, even the internet itself. C4ISR and logistics support all focused on performance. Aerospace, check that, Northrop Grumman is divided into 4 operating sectors. Aerospace systems is the sector I work for or work in. We have a sector called electronic systems, we have a sector called information systems, and we have a sector called technical services. And you can see there's quite a bit of different products and service we provide in each one of those sectors. Aerospace systems, we're divided into basically 3 areas in aerospace systems. In the unmanned systems, we provide the Triton, which is a Global Hawk derivative. We also provide Global Hawk and NATO air-to-ground surveillance and Eurohawk, so we're providing this great unmanned platform to fly at high altitudes to do reconnaissance. The whole idea about UAVs is to pilot out of the threat zone, for example, and provide long duration capabilities. Pilots get fatigued, and so if we can cover longer durations in the air, we can provide more sensors on targets, for example. The UCAS system is the newest technology that the Navy's pursuing to look at aircraft that can actually fly onto an aircraft carrier that's unmanned and basically land and take off on an aircraft carrier. And we've done that, demonstrated that. And we also have some smaller platforms, the Fire Scouts and Firebird for the Navy. Military aircraft systems, oh, and by the way, unmanned systems is located on the West Coast, primarily in Rancho Bernardo, in the center of excellence there. Military aircraft systems is the area that we work here, but we have it spread out geographically. The B-2 bomber, which you're all probably familiar with, and the E-2. The E-2 is the Navy's version of a aircraft that can search for targets at long distances with the high technology radar to see various targets at distance. It's similar, very similar to the AWACS aircraft, this one being for the Navy, and it can land and take off on an aircraft carrier. So it provides the aircraft carrier fleet that capability to protect itself from long-range targets.
Buys in minutes of protection.
Buying minutes, because it's also looking for cruise missiles that might be coming out of the aircraft carrier, and how are you going to try to deal with that particular threat. Joint STARS is done here, the engineering and development that we do, and that's got a large radar on that, so it can look at ground movements. So it's primarily in support of the Army, to look at various ground movements of people in the Army, and providing that to the tactical commanders in the field. F-35 is the most important aircraft, fighter aircraft development program going on for the country. That's the newest aircraft that we have that will eventually replace the F-15s and the F-16s. And we provide some support to Lockheed on this with the structures. We're a major contractor with Lockheed Martin being the prime contractor on the F-35. And there's some other incidental systems, electronic attack on some of the older aircraft, the F-18s and the Growlers. And then there's laser weapons that kind of ironic to fall under military aircraft systems, but it's to attack those aircraft that might be coming at a naval target. And finally, space systems. There's some classified systems. We do communication systems, geoint sensing and science, and missile defense and advanced missions, and the various aerospace products that go with that. So it's a pretty exciting portfolio that we have in aerospace systems this time. We have some centers of excellence that we're standing up, and it's exciting to say we're standing up our own center of excellence here. And this is great because it's good for Florida, and it's good for this greater area of Brevard and reaching down into Bureau counties and maybe even up north, where this will become the Manned Aircraft Design Center of Excellence. Design, where St. Augustine's more manufacturing or integration, we're going to be the design center of excellence for manned aircraft. And that's exciting because we're standing that up now, and it's going to be very, very exciting for this area as this center of excellence grows over the next years to come. There's also a center of excellence for electronic attack up in Bethpage, and then on the west coast are centers of excellence for aircraft integration there, and the space systems, and San Diego, which I mentioned, for the unmanned system center of excellence. Here's just a few miles from here, right? So if you think about this picture, Florida Tech would be somewhere up here, I think. And we have this facility here where we have a large hangar next to the Melbourne Airport, and we do some work on the joint stars here. This is the integration and test facility. Sometimes we have a couple joint stars aircraft parked here on the tarmac here where we're working on integration. We have these other incidental buildings. I work in this particular one for those ISR programs I mentioned earlier. And we're building a new building this year. And it's under construction. It's well underway. The whole shell's put up. We're already starting to put all the systems in it. And we're allocating all the various infrastructure to that. And that's where we're going to bring the E2 down and do all the design work associated with the E2. And the E2, the Navy's planning on ordering probably up to, I believe, 40, 45, maybe perhaps 50 E2Ds, the advanced Hawkeyes, in support of the Navy's carrier fleet. So this is exciting that it's going into production. We built up in St. Augustine, but an aircraft like that constantly needs to be looked at in terms of opportunities to insert new technology that might come along, and we'll be doing that and the engineering associated with that. So like I said, that building is coming up. All right, Science, Aerospace Systems Engineering, right? That's what we want to learn a little bit about. Architecting a whole that is greater than the sum of its parts. Engineers, they come in different sizes and shapes, don't they? There's structural engineers, there's chemical engineers, there's civil engineers, there's electrical engineers, there are aeronautical engineers, there's even materials engineers, there's computer engineers, there's other electrical engineers, there's acoustic engineers, mechanical engineers, but there's also systems engineers. And a lot of folks like, well, I know most of these, but what in the world is a systems engineer? Well, let's figure that out. What exactly is a system? Anybody? What exactly is a system? Right? I like to think of it as it's the whole that's greater than the sum of the parts. We can think of a system as, well, that whole integrated aircraft, or maybe a space system, for example. Maybe it's an industrial facility, that's a system. Maybe it's an IT system. But what exactly is a system? Well, fortunately, it's defined. Now, I don't want to have to read this, but you can see that there's a couple things there. The elements include hardware, stuff that you can feel, right? Hardware. Software, all those bits, all those ones and zeros that go into making code. Facilities, you need facilities to support a system. It's part of the system. People. People are part of the system. Policies, rules and procedures to operate things, and information. The results include system level requirements. So if we define a system, we got to have the requirements associated with that. We got to understand the properties of the system. We got to understand the characteristics, the function, behavior, and performance. That's a tall order. The systems engineers have to try to get their arms around that. They have to try to understand all those kinds of things. We're looking at all these elements and how they interact with each other, how they interplay with each other, interfaces, requirements, and so forth. It's the International Council of Systems Engineering that has defined what a system is, and this is sort of that leading edge organization that deals with systems engineering. So if somebody wanted to become a systems engineer, this would be one of the first places they would start to learn about what is systems engineering. Okay? I like to think of it as big picture thinking. So it looks at all these different elements, right? People, processes, tools, policies, all these different elements. Where do you start? How do you even deconstruct that? If you're responsible for a system, how do you even start to deconstruct what that is? Where do you go? What do you do? What's the first thing you need to do? Well, you have to get your mind wrapped around the idea of systems first and understand what they are, and then you start to decompose. You break it down into simpler pieces, right? And you start to try to put things together, like, well, there's systems, components to systems, there's the technical aspects, and there's the operational aspects. And they all kind of work together to some degree. And it gives a person a start, trying to figure out, okay, what do I need to do as a systems engineer? I got to come up with requirements, and I got to decide what those requirements are, what are the features, what are the benefits, and so forth. And how's the technology supporting that, and what's it going to look like from an operational point of view. So what do modern aerospace systems all have in common? Modern aerospace systems all have some common characteristics. They're becoming increasingly complex. We all get that. Hence the big push for STEM. If we don't have STEM students going in this, we're just not going to get there. They require human operators to operate or monitor. They require software to provide desired functionality within the system. Modern aerospace systems have embedded computers and microprocessors. They're highly interactive, and they have these complex interfaces between all those elements we talked about earlier. We want to use limited resources. We don't have unlimited budgets to do systems anymore. Maybe we did a while ago, but we don't. National security requirements are always balanced with the available dollars available. We're doing that right now. We're looking at decreasing national security budgets. But we still have requirements for these complicated systems. New technology may be required or desired. How we incorporate what the new technology is that's coming out of R&D labs, for example. How we embed that into these modern aerospace systems with the limited resources available. They have to be highly reliable and long life. We don't want to spend billions of dollars in developing a new system that only lasts for 2 or 3 years. They have to last much longer than that. The B-58 Hustler that I talked about earlier when I was a kid. I mean, we spent, I don't know what this country spent on that, but it was operational for like 5 or 6 years. And technology probably wasn't ready yet. We used to call that airplane the Widowmaker. Why did they call it the Widowmaker? Because if you're going supersonic in that airplane and one of the engines failed, the airplane would go sideways. The pilot wouldn't have hardly any time to react to that airplane going sideways. It would just disintegrate. So then they have to start flying at that subsonic speed. Well, it was a high altitude supersonic bomber flying at subsonic speed. It didn't even meet its requirements anymore. They finally retired it. Finally said, that's it, we're not going to do it anymore. We can't have that. We can't have those kinds of investments anymore in these increasingly complex aerospace systems and not have the high reliability and the long life that we like to get out of that investment. we're all taxpayers, we don't know what we're doing here. Design and development requires systems engineering. There's no way about it anymore. You can't do this independent of systems engineering. So where did it all start? It really started with Lockheed Martin. Skunk Works, Kelly Johnson. We all remember history-wise, I think many of us know when Terry Powers was shut down in U2, right? Many became a prisoner, more or less. There was a big push at that point that we can't allow this to happen. And it was the Skunk Works folks that came out with the SR-72 in short order, and it was these outstanding individuals and small groups that came up with this idea of technical management processes to go from idea to conceptual design to requirements to more firm design to preliminary designs to then actually critical designs and creating product and putting it and testing it and getting it. And they did this in very short order. It became a very successful model to follow. The tools were all developed in those early 60s to basically decompose, break down those complex aerospace systems into simpler and simpler elements to the extent they could. Single designer is not capable of total system knowledge anymore. It's a divide and conquer. And the systems engineer's idea is to sort of be the glue that holds it together, because you can farm out lots of pieces to different people in these complex systems, but there's the ability, or you need the ability to hold that glue together. And engineering specialization glued together with systems engineering. Systems engineering would help all the specialties, like I talked about in MB2, to bring all those folks together to understand the interactions between those various elements. Current DoD interoperability and systems of systems integration is driving the next advancement. The ability to have joint interoperability. No more, the idea presumably is, if the Navy isn't talking to the Army, and the Army's not talking to the Air Force, and the Air Force is not talking to the Marine Corps, that's not good for us. We can't afford those kinds of things anymore. We need joint interoperability, and that's the next drive for systems of systems.
When you say interoperability, I'm taking that to mean that the Navy could use it, or the Air Force could use it, or the things that are developed could be slightly modified
Yes.
to meet those requirements.
The F-35 is a classic example, right? The F-35 is a joint attack fighter that can be used for both the Navy and the Air Force. The Air Force and the Navy now have a common airframe, and even the Marine Corps can start to use it. And yes, some requirements will change, but maybe the airframe is common to all the joint services, and therefore you get a benefit of a large quantity of order to try to lower the cost and use that. But interoperability also is, there's an AWACS talking to a guy on the ground, and there's a commander able to direct a land-based attack, for example, things of that nature. You don't want the Navy just having a silo-based Navy operation or Air Force operation. You would like them to improve interoperability. I'm not saying they don't already communicate with each other, but there's always there's always an opportunity to improve communications amongst the services, especially when you're deploying various weapon systems. Today's aerospace systems engineering. Systems engineers engineer the system. The structured process to ensure the system meets all of its requirements. Define the system, design the system. The systems engineers don't build it, right? So they define it and design it to some extent at the systems level. Then the systems get built, and then they come back and help integrate it, test it, and support it over its lifespan. And that's what a systems engineer's career would look like. He would start out with what are the requirements, and then he would be part of reviewing the design. But then it would go into the manufacturing phase, and the system would be built. And then it would come back and start to integrate the components, the elements, the sub-assemblies into the broader system. And then it would test it, verify the interfaces are working properly. And then eventually, once the system is deployed, and our warfighters are using it, for example, or space agencies are using it, or a space system, that they can support over the lifetime of its program. In other words, aerospace systems engineers bring it all together, bringing the technologies together, looking at the various technologies, for example. What are the spaceborne electronics, or thrusters, or advanced structures in terms of this being a space program, precision gimbal drives, phased arrays, all these kind of technologies, looking at those, come together then into a specific space mission system in this example. But it's all to support missions, right? The mission being weather climate monitoring. Well, what do we need to bring that about? Well, we need to bring about a satellite system that can look at weather and climate monitoring. Oh, what's a satellite system? Well, it's comprised of all these individual elements. And it goes along that route for systems engineering. Aerospace systems engineering roles. How are we doing on time, by the way?
You got about 7 minutes.
Okay. Technical leader responsible for the success of the system. He defines or she defines and manages requirement sets that are comprehensive, validated, verifiable, and traceable. And that's what a systems engineer do. There'll be a lot of writing and technical requirements and managing those requirements, especially in change processes and so forth. He designs systems, or she designs system solutions that balance across competing priorities. So now he's also going to be kind of the arbitrator between need and performance and risk and cost and schedule. So the mechanical engineer might have one way of doing something, the electrical engineer might have a different way of doing something, acoustic, so forth and so on, and the system engineer is going to try to arbitrate where there's some interface issues or there's some challenges across those interfaces.
You determine the critical path.
Critical path in terms of scheduling, looking at what it's going to take, because there's requirements to get these systems deployed, for example. He or she decomposes a system individually into individually implementable elements. So again, looking at it abroad, you got to divide and conquer and keep on lowering it down to the lowest level you can so that you can build it and test it and verify its requirements are met, and then integrate it more and more into the broader system as it goes along. And then he integrates the engineering effort across programs and brings disciplines together to fill those gaps. So he is the glue that holds it together. The systems engineering approach requires a top-down, bottom-up development approach. So top-down to view the system as a whole, and bottom-up to determine those trades and the performance feasibility and the allocations of those requirements. So a systems engineer has a top-down view, and he also has, at the lowest level, a bottoms-up view. And that's a kind of an interesting concept. It's kind of a V, top-down and bottom-up. He also, or she also, looks at the life cycle of the system. So he has to have an orientation to ensure decisions are made that consider the impacts of not only development, but operations, and maybe even disposal. Think about it. How are we going to dispose of the space station when the time comes? At some point, you can't just leave it up in orbit. A systems engineer would actually think about what's the end game for the space station, for example, in terms of controlled re-entry over the ocean so that it doesn't impact an environment as it's disintegrating, right? I mean, and that's the largest space structure we've ever built in the history of the human race. We got to dispose of it. The systems engineer is looking at that end game, not only getting it out there and getting it in theater, but also the disposal of it.
So, eBay.
Parts available on eBay, right? Retrieve those parts. He or she's focused on system requirements and system performance baseline. So he baselines the performance, the weight of the system down to the allocated level, or product that a mechanical or electrical engineer needs. I got to design a circuit board. I don't know how many pounds do you give me to design that circuit board? It's a total allocation. Because at some point, it has to be, an airplane has a limit on how much it weighs based on its design, and there's all those trades that go into how they're going to do that. And then the systems engineer needs to allocate individual weights, for example, to each person that's not designing a component of that system, and then has to measure. That's your baseline. And if the one engineer goes over his weight, and you can't raise the total weight, the system engineer is going to have to find somebody that, hey, can you shave a few pounds off over there? No, it's company called U.S. Chemical. Wait a minute, it went back. They got to have some multi-domain experience, right? And they have to have a knowledge of how the system will be built up and how they can test it. It's one thing to have all the requirements and allocate all the requirements, but how do you validate? How do you verify and validate those requirements are actually implemented? So you got to have test plans that allow you to look at that. Okay, here's my product, here's my black box, test it. Well, you have requirements, so there would be some functionality associated with that black box, and they would want to test it. And the systems engineer would be part of testing that. And knowledge and experience knowing how to test it. It's the big systems engineer model B. It's like a V. Top down, bottom up. Customers' needs, driving it all the way down to where it's actually built, and then testing it right up and showing that it meets customers' requirements. The systems engineering model B is what we call it. So, aerospace systems engineering helps program managers find the right balance, right? There's needs and requirements, there's cost, there's performance, there's risk, and there's schedule. Anybody know which side of the building you were attacked on 9/11?
Left side.
Which one?
Cost side.
Which one? Which side? Cost. No? No?
Needs and requirements.
We only got 2 more to go.
Risk. Risk. Right? Were we prepared? Were we prepared? Well, one would argue we weren't because we were attacked. And what happened there? And of course we responded, and we've been responding ever since with capabilities to do what we need to do to try to mitigate the risk of another attack. Future systems engineering challenges, I'll quickly wrap this stuff up now. Increasing system complexity. Things are getting harder all the time, folks. We all know that, right? We're challenged in the classroom, I'm sure, to some degree. We're challenged in the industry that things are getting more complex versus complicated. And they got to have, the systems engineer has to have some fluency in both hardware and software. It used to be divided. Broader range of missions, from small to large space structures, and from lighter than air to next generation long-range strike. B-52, by the way, it's going to be 100 years old when it finally gets retired. That's 100 years old. Well, I know pilots, I'll volunteer to fly a B-52. I mean, I don't even know if we get pilots to join if they have to fly a 90 or 80-year-old airplane. Economic pressures demand increased cost affordability. We're in that environment. We're always in that environment, right? And then finally, consistent systems engineering implementation from system down to segment, element, subsystem, all those kinds of things. Some of you might have heard this one, right? Systems of systems. Kind of a buzzword out there now. Systems of systems? Is that part of that complex activity? Absolutely. This way, MIT professor Donna Rhodes says about systems. Global engineering environment drives a new worldview, systems of systems, evolving needs, new approaches, and advances in technology are influencing the characteristics and capabilities of emerging and future systems. Systems of systems are comprised of several autonomous, embedded, complex systems that can be varied in geography, operation, context, technology, and conceptual framing. So a spacecraft, it's a system by definition. A launch complex could be a system of systems because there's so many interrelated parts based on that. And the significant challenges going into the systems of systems framework is optimizing that mix of all these independent systems that are working and all those challenges I just talked about with systems engineering, and operating that system of systems, or systems of systems, in an uncertain environment, and the interoperability again between those independent systems. So now it's exactly more complex with this kind of framework as we go into the future. Types of students that rise up as systems engineers. You want a degree in aero or astro or a mechanical engineer, electrical or math or physics. So there's not like a systems engineering degree. Well, actually there is now. So aerospace engineering typically, astrophysics typically, but now there's even master's degrees in systems engineering that do that. They're big picture thinkers and prefer to work in a team environment. They like science and engineering and enjoy working directly with customers. They like to work on cutting-edge aerospace and defense systems, and they like to be sitting at the console coming down a launch of a 4.5 million pound rocket, right? So they, hey, that's my system. I'm part of that. I helped design and develop that. It's the mechanical engineer. Well, I got a component on there, but the system got the whole thing. She was part of the whole thing, and so they tend to like when the first flights of anything, they get the, wow, that's my system. I was part of it. All right, I'm going to wrap it up. Our commitment to STEM, I did leave you something in the brochure where you can reach back into Northrop Grumman's corporate website where you get a lot of this information as well. You all probably know this more than I do as teachers, right? Our kids are boarding things. You don't know about it? Maybe? It's a difficult discipline. 41% of teens associate the word difficult with engineering. It is difficult, right? It is. Especially in this day and age now, kids have this phones and games, they're constantly doing the technology, and they're out there. How much time are they spending on homework, assignment, and really studying and learning this stuff? It's a challenge. They're not prepared for college engineering. And I'm an example. I didn't take advanced math and science in high school. Like I said, I took algebra 2, trig, but I didn't take calculus. I regret that. I had to catch up later. And so they're not prepared for that college level engineering. And maybe it's ineffective messaging. Maybe that's part of the problem, right? Engineers solve problems using math and science. Wow, that's what I want to do. I want to be engineers solve problems in math and science. Oh, wait. It's essential to our health, happiness, and safety. Maybe the message is wrong. Aerospace engineering with benefits, huh? Right? Love your work and live life too. Get to be creative. Work with great people. Design things that matter. Maybe you don't want to design defense systems. Maybe you have a problem. Well, there's space systems too. There's national space systems. There's industrial systems. There's all kinds of things that can contribute. Energy systems and so forth, where engineers can contribute. They never are bored. Never get bored of this stuff. They make great salary, actually. You all know that. They get some job flexibility. They get to travel. They get to make a difference. They get to change the world. And some of them get to sit at a launch console helping launch a 4.5 million pound rocket. I did have an opportunity to do that a few times. That was really cool. And I did make a mistake once. Yeah. We had to power down the orbiter. I forgot to configure, tell the crew commander to configure one of the switches. It was in my procedure. It was on the next page. Never got to the next page. I forgot about that. That's just life. Humans make mistakes. We learned our lesson, right? We moved that particular step to the page up. What's our STEM pipeline with Northrop Grumman? Like I told you earlier, we start at preschool and we go through middle, high, and college. We've got lots of programs to get kids involved right through college. These again are national programs that are available to teachers like yourselves to access, to point students into these directions on other opportunities. have it in them. It can be very meaningful and personally rewarding for them. Our world does have some big problems, and engineers are going to be expected to solve some of those big problems. It does require discipline and a good deal of effort. There's no doubt about it. It's hard. Edison was said ingenuity is 1%. 1% inspiration and 99% restoration. It is hard, right? I mean, you're probably challenging some of the students. Wow, we might have been talking about engineering when you said that. Engineering degrees are held by more CEOs than any other field. It's probably not true of the chief technical officers as well. And 62% of all CEOs have advanced degree, either an MBA, PhD, law degree, or master's degree. Value of performance, Northrop Grumman. It was a real pleasure to talk to you tonight. I hope you